Okay, so the Babylonians used a base 60 system, and the way this works, they really only had two characters for numbers. So they had these downward triangles, which were their ones, and they had these boomerang-shaped characters that represented 10. But the way they created larger numbers is they had this kind of like a place value system. It is a place value system. It's kind of like the one that we use. If you took one of these shapes, for example, and put it right here, this would just be worth 1. It's a 1, it's worth 1. It gets multiplied by 60 to the 0th power, but anything to the 0th power is just 1. So that one's worth 1. If we put another one there, now our entire number is 2. If we throw a 10 in there, now we have 12. 10 plus 1 plus 1. So this is all good and fine. Then what we can do is move over here to the left. They didn't have boxes. They just put spaces in between their different places, and I'll show you how we can do that at the very end. So let's say we put a 1 here. Even though this character is a 1, by being in this second group over here, it gets multiplied, so it's more powerful. And in fact, it gets multiplied by 60 to the 1st power, which is just 60. So every time we put 1 here, it's worth 60, even though each one of these ones is just worth a single 1. If that sounds strange to you, think about how we do in our system, where if we have, say, the number 2, it's just worth 2, and yet if we have the number 23, that same symbol that was representing 2 up there now represents 20, right? So it's the same idea here, where this single triangle represents 1, this represents 60. If we put 1 right here, any one in this box is worth 60 squared, or 3600. So this symbol is now worth 3600. If we put a 10 there, each one of those 10 would be worth 3600. In other words, the value of this symbol would be 10 times the multiplier of 60 squared. So 10 times 3600. So this piece right here is worth 36,000. 10 times 3600. Whereas this one right here, which looks identical, but is shifted over in their place value system, would only be worth 10 of the ones. And then if you delete all this, this is how their number would show up. So you'd know that over here we have 10 plus 1 plus 1. This is just 12 multiplied by 1, but that's just 12. This one right here is worth 60. 1 times 60. Here we have 10 and a 1, so we have 11 times 3600. If we added all that up, we would get the number that we have here. So let's do a little bit of practice with these here. So let's say we had this Babylonian number and we want to figure out what it is in our Hindu-Arabic system. So we start over here. Let's go left to right. It'll be easier when we convert the other way. So let's try to figure out what these two symbols are worth. It's 1 plus 1. So this is a 2, right? 2 of these 1s gives us a 2. But it has a multiplier, right? It's multiplied by 60. So we have 2 times 60. So together, this part of the number is worth 120 already. This one's worth 60, and this one's worth 60. We have 2 of these 60s. Now we move over here. Notice we have a 10, and then 2 1s. This would give us 12. And then that's going to get multiplied by 1, so it's going to stay 12. We're going to add that to what we already have. Doesn't matter if you have this times 1, I'm just putting it in there for consistency. And if you work that out on a calculator or on the scratch paper, you should come up with 132. So this Hindu-Arabic number right here, and again, it would look like this. You wouldn't have the bars in there, but that would stand for 132. Notice that it's a little bit ambiguous, because if you see these characters right here and you don't have the boxes like we have the benefit of doing right now, it could just as well be this number, right? If you don't have the benefit of having the boxes here, you can't tell any difference between that number we originally saw and this number right here, because they didn't have any placeholder for 0, and that's important. In their original system, later on, they developed a symbol for 0, which was important because it helped tell the 132 from this number, which would be much higher. We'd have each one of these is worth 3,600, which is already far above the 132. So it is important to note that there was a little bit of room for grayness in their system because they didn't have that 0. Let's try another example. So here we have a spot where there isn't any symbols. Let's see how that plays out. Over here we have 2 of these 10 characters. In other words, we have 20 in this box, but each of those 20s is worth 3,600. In other words, if we want the total value of those 2 characters, we have to take 20 times 3,600, and that would give us the value of these 2. There's nothing here to add, so we move over here. Here we have a 10 and a 1, that's 11. That'll get multiplied by this 1. So let's add 11 there, and if you work this out on a calculator or on scratch paper, you should get 72,011. Okay, and again, their actual system would have looked like that without these little lines here, right? So there would have just been a really big gap there, hopefully. But again, a little bit ambiguous. You can't tell if these 2 are here or if they're over here. That's the importance of 0, and that's the thing that the Babylonians were missing here. Let's try another one. So go ahead and pause the video and see what you think this one would be. Okay, here we just have 1, and it's getting multiplied by 216,000. So 216,000, sorry, 1 times 216,000 would give us 216,000. So that single character there suddenly becomes much more powerful than when it was sitting right here. So if you just saw a single 1 sitting around, how would you know if it was worth 1 or whether it was worth 216,000? And you wouldn't. In their original system, this was a major shortcoming of their system. Now let's try the other way. So let's say that we know our Hindu-Arabic number, 63 here, and we want to put it into the Babylonian system. So the way we want to do is we want to start from the left and get out as big of a number as we can. So for example, if we could fit 216,000 into the 63, or maybe we could even fit multiple ones, we would try to do that. But we certainly can't pull 216,000 out of 63. Same with 3,600. Doesn't go into 63. 60, however, we could pull a 60 out of there. So let's do that. By putting a 1 in here, we've now represented 60. So in other words, 63 minus 60, we've already put the symbol for 60 out of our original 63, and we have 3 left that we need to account for. Well, we're not going to get any more 60s out of that 3, but we could represent that with 1s. So let's put 1, 2, 3. And if we delete this, notice there's this gap in between them. So if we wanted to write 63 in Babylonian, it'd be this single wedge shape, and then a space, and then 3 wedge shapes. Okay, something a bit harder here. Maybe pause the video, see if you can take a stab at it first. So again, starting from the left, and notice that this box continues. We'd have 60 to the 4th, 60 to the 5th if you had a really high number you wanted to deal with. We won't do that just because it would get tedious in this class. 216,000 doesn't go in there, so we don't have anything in this box. 3600s though, we could get some 3600s out of there. In fact, just one. But once we take one out of that, we're going to subtract 3600, and that would give us 243. In other words, our goal was to represent this would be the final amount that we're trying to represent. We've already, by this single wedge here, we've already represented 3600 out of that 3843 we need to represent, which means we have 243 we still need to represent. Notice we can't get any more 3600s there. If we put another one there, we'd go way over our 243. So we go down to the 60s. How many 60s would go into 243? Well, you can work that out, long division, if you want to use a calculator. Either way, you'll find that you'll be able to get 4 of those 60s. So let's go ahead and put 4 of these ones. If you guess too high, you'll get a number that goes over the 243 and you know you need to scale it back. If you go too low, let's say you only put 3 in here, it'll naturally take care of itself, because when you subtract, you would get a number that's still bigger than 60, so you know that you could still take some more 60s out. In our case, we took 4 of these 60s here. That would give us 240, which means of our original number, we've accounted for 3600 here, we've accounted for 240 here, but we still have 3 that we haven't represented yet. So let's go ahead and put those ones in there. And that would be our number here. If we delete this, this is what 3843 would look like in the Babylonian system.